All right, we'll get started. Thank you, everyone. So good evening, and welcome to the 34th Annual Robert Hofstadter Memorial Lecture, hosted by the Department of Physics. I'm Peter Michelson. I'm the chair of the lecture committee this year, and it's my pleasure to welcome all of you. This year, our distinguished speaker is Professor John Preskill from Caltech, where he is the director of the Institute for Quantum Information and Matter. And I heard a story, I'll tell more about John in a moment, but I learned today that originally it was called the Institute for Quantum Information. And then eventually they actually had some experimentalists join that brought some matter into that.
That's true.
Okay, he can tell you more about that. But I'd like to start just to say about the person that this lecture series is in honor of, Robert Hofstadter, who's really a legend at Stanford, tremendous impact on, I think, a number of people in the audience. So I'll just talk about my own personal experience with him a little bit. When I was a graduate student here at Stanford, he was not my advisor, but he was not my official advisor, but he was somebody I always felt free to knock on his door and get advice. And he was always very welcoming, just really tremendous to know him. And Bob Hofstadter had a very long career, started, I think, at Princeton, and then eventually he came to Stanford, where he did some very important measurements of the structure of the proton, for which he received the Nobel Prize in Physics, shared with Rudolf Mossbauer in 1960. And then after that, Bob, he had broader interest in just particle physics. He was very interested in many areas of science, and one in particular, which meant a lot to me, was he also had an interest in astrophysics and astronomy and what was going on in the sky above us. And so Bob pioneered a project that unfortunately he did not live to see launched, which was known as the Energetic Gamma Ray Experiment Telescope, EGRET, which flew on an observatory that NASA launched in 1989 or 1990. I've actually forgotten what year it was. I joined Bob's group. He invited me to join it when I joined the faculty here at Stanford as an assistant professor. And his advice to me was, do something different than what you did your thesis on. Which I thought, yeah, this is interesting. So I think in many ways that was good advice. But Bob was always interested in new ideas, and he was also could be quite a critic, but in a very engaging way. And for that, I deeply appreciate that, what he brought to me. And so, anyway, to make a long story short, EGRET got launched, and it was a great success, and inspired mostly by Bob Hofstadter, but also just the findings from the EGRET and the Compton Observatory, which was in orbit for, I think, about 9 years. Working with some colleagues at SLAC, I had more to learn. So I went to SLAC and learned, hey, what's the next great thing we should do? What technologies are available? Which Bob, I'm absolutely certain, would have agreed with. And so that led to a collaboration which grew and grew. And eventually we developed what's now called the Fermi Gamma Ray Space Telescope, which has now been in orbit for 15 years and is still operational and doing great stuff. And I think Bob would have been extraordinarily pleased with that. So we should have probably called it the Hofstadter satellite, but anyway, it's known as the Fermi Gamma Ray Space Telescope. So I know that Bob, now let me turn to John, who's our speaker this evening. John Preskill was a graduate student at Princeton, I've forgotten when,
Undergrad at Princeton.
What? Oh, sorry, you were an undergraduate at Princeton. I got this wrong. he was an undergraduate at Princeton, and from what I understand, at the end of when he got his bachelor's degree, he thought, what do I do next? And he decided to go to Harvard. And at Harvard, he worked with, his thesis advisor was Stephen Weinberg, that he worked with for a number of years. And then from Harvard, John went to Caltech. Now, he did some very, really important work in particle physics and actually understanding some things about monopoles that were, Roger Blanford mentioned yesterday, that were really quite impactful on a number of areas of astrophysics, including some of the motivation for inflationary cosmology, which has been absolutely revolutionary. So John was part of that. And then at some point, John said, okay, I'm going to change direction. And he started looking at quantum information and quantum computation. And so this evening, he's going to talk to us about that. So his lecture is Quantum Computing and the Entanglement Frontier. So I think we're going to get very entangled in this. But, and I just will read the last line of the abstract that he wrote for his talk. He said, Preskill is less weird than a quantum computer and easier to understand. So he's going to speak to us, and we can decide whether he's actually easier to understand. John.
Well, thank you for the kind introduction, Peter. It's always exciting to be at Stanford, one of the great centers of the world for physics research, and I'm especially honored to be the Hofstadter lecturer. I admire greatly the achievements of Bob Hofstadter that Peter reminded us about. I remember the excitement that I felt as a student when I learned about his pioneering experiments to explore the structure of the proton with electron scattering. So I'm honored to be giving this lecture. It's going to be a talk about quantum physics, but it's also about information. We all recognize that information technology now has a huge impact on our daily lives, but we're also aware that the technology that seems impressive today is going to be replaced in the future by new technology that we really can't imagine today. But it's interesting to speculate about future technology. I might not be the best equipped person to engage in that type of speculation. I'm not an engineer, I'm a theoretical physicist, and I can't claim to be deeply knowledgeable about how computers really work. But as a physicist, I know that the crowning intellectual achievement of the 20th century was the development of the quantum theory, and it's natural to wonder how the emergence of quantum theory in the 20th century is going to impact 21st century technology. Quantum theory is an old subject by now, but some of the important ways in which quantum systems are different from classical systems, by which I mean non-quantum systems, we've come to appreciate more deeply only relatively recently. And those differences have to do with properties of information carried by physical systems. To a physicist, information is something that we can encode and store in some physical system. But fundamentally, we know all physical systems are really quantum systems governed by the rules of quantum mechanics. And so information is something we can encode and store in a quantum state. And information carried by quantum systems has some notoriously counterintuitive properties. That's why we sometimes speak about the weirdness of quantum theory. And physicists relish that weirdness. We take great pleasure in it, but in recent years we're taking more seriously, both physicists and engineers are taking more seriously that we might put the weirdness to work to exploit the unusual properties of quantum information to do tasks that would be too hard to do otherwise. And that desire to put the weirdness to work has driven the emergence of a field that we call quantum information science, which derives a lot of its intellectual vitality from three central ideas: quantum entanglement, quantum computing, and quantum error correction. And the goal of the talk is to explain those ideas. So let's start at the beginning. We know that any amount of ordinary classical information can be expressed in terms of indivisible units, bits of information, where we could think of a bit as an object like a ball, which could be either one of two colors like red or green. If I want to store a bit, I can put it inside a box, and then later on when I open the box, the color that I put in comes out again. So you can recover the bit and read it. And for some purposes, it's helpful to envision quantum information carried by quantum systems, as being composed of indivisible units, quantum bits or qubits, where we can envision the qubit as, again, a colored object which is stored inside a box, but where now the box can be opened through either one of two possible doors, labeled door 1 and door 2. Those two doors correspond to two complementary ways. We could store information in the box or read out what's inside the box. And if we encode information in a qubit through either door number 1 or door number 2, and then later we open that same door again, if we observe the qubit in the same way that we prepared it, then the color that we put in comes out just as though it were a classical bit. But if instead we put information in the box through door number 1, and then later on we open the other door, we observe the qubit in the complementary way, then what will come out of the box cannot be predicted. It's random. It has an equal chance of being either red or green. And so in order to read the quantum information, you have to do it the right way. And if you do it the wrong way, you will irreversibly damage the information that was put inside the box. You can appreciate one consequence of that if you think about copying quantum information. What would it mean if we had a quantum copy machine? It would mean that if I happened to have put information in the qubit through door number 1 and then made a duplicate of the box, if I opened door number 1 on the original and the duplicate, the color that I put in would come out of both boxes. And alternatively, if I happen to have stored information through door number 2 of the box and then made the duplicate qubit, if I opened door number 2 on the original and the duplicate, the color that I put in would come out of both boxes. But in fact, no such machine is allowed by the principles of quantum mechanics. We can't build a machine which builds a high fidelity copy of an unknown state of a qubit. And the reason why not is that in order to make a copy, the machine needs to probe inside the box. And if it happens to guess right and use the same door that I did, it could copy the information just as though it were classical information. But if it makes the wrong guess and opens the wrong door, it will irreversibly damage the information. And then there won't be any way to make a high fidelity copy. So although we might envision cloning a sheep, we can't clone a qubit. Now, as you see, I like to think about qubits in an abstract way, but a qubit is always instantiated in some physical system, and I'll mention some other examples later on in the talk. But just so you have something concrete to envision to begin with, we could have a qubit encoded in a single photon, a particle of light. The photon has an electric field that oscillates back and forth. And the two states that I described as colors, when we observe the photon through door number 1, correspond to the electric field oscillating either horizontally or vertically. But I could also consider, and this is what it means to look through door number 2, the direction of oscillation along these 45-degree rotated axes. So what I'm claiming is that I could prepare a photon which has this horizontal polarization, and then later if I observe the direction of the oscillating electric field along the rotated axes, I just generate a random bit, and it can't be predicted in advance what I'll see. Now, the really interesting differences between quantum information and classical information can't be appreciated unless we consider systems of more than one qubit. So let's suppose we have two qubits, and they could be far apart from one another. Let's say one is in my lab at Caltech in Pasadena. The other is in the custody of a friend of mine in the Andromeda galaxy. And a long time ago, these two qubits were both on Earth, and they interacted in some way so as to become correlated so that the pair of qubits has some interesting properties. Namely, I can open my box in Pasadena through either door 1 or door 2, and either way, what I see is just a random color, which has an equal chance of being either red or green. And the same is true for my friend in Andromeda. He can open either door number 1 or door number 2 of the qubit and just sees a random color. So neither one of us, by opening the box in Pasadena or Andromeda, acquires information about what's inside the box. We just generate a random bit. And that's kind of peculiar because with two qubits, we should be able to store 2 bits of information. So we could ask, where is that information hidden in this case? And the answer is, for this particular correlated state of the 2 qubits, the information resides entirely in the correlations between what you see when you open the box in Pasadena and open it in Andromeda. Because it turns out that if I open door number 1 and my friend opens door number 1 for his box, then we always see the same color. It could be red or it could be green, but it's guaranteed to be the same. And the same is true if we both open door number 2. We're guaranteed to see the same color, maybe red, maybe green, but always the same if we open the same door. Now, there are 4 distinguishable ways in which a box in Pasadena could be correlated with a box in Andromeda. We could see either the same color or different colors when we both open door number 1 or we both open door number 2. And by choosing one of those 4 possibilities, we've encoded 2 bits of information in the pair of qubits. But what's unusual is that that information is not accessible locally when you open the box in Pasadena or in Andromeda. It's encoded entirely in the correlations between the 2 qubits. And that property of quantum information, that it can be shared non-locally between distantly separated objects, is what we call quantum entanglement. And it's the really important way in which quantum information differs from classical information. Correlations themselves are not unusual. We encounter them all the time in daily life. I normally wear 2 socks that are the same color, so you can look at my left foot and then you know for sure without looking what color to expect on my right foot. And it's rather similar with the boxes. If I want to know what my friend is going to see when he opens door number 1 in Andromeda, I can open door number 1 in Pasadena to find out. Or if I want to know what my friend is going to see when he opens door number 2 in Andromeda, I can open door number 2 in Pasadena to find out. So you might suspect that the boxes are really just like the sockses. But I insist the boxes are fundamentally different than the sockses. And the reason is that there's just one way to look at a sock. But because we have these different complementary ways to look at a qubit, the correlations among qubits are richer and more interesting than correlations among ordinary bits. This phenomenon of quantum entanglement was first explicitly discussed by Einstein and collaborators nearly 90 years ago. And to Einstein, quantum entanglement was so unsettling as to indicate that something must be missing from our current understanding of the quantum description of nature. And that paper elicited some thoughtful responses, including a particularly interesting one from Schrödinger. And the way Schrödinger put it is that the best possible knowledge of a whole does not necessarily include the best possible knowledge of the parts. And what Schrödinger meant by that is that even if we have the most complete description of the pair of qubits that the laws of physics will allow us to have, we are powerless to predict what will be seen when we open the box in Pasadena or Andromeda through either door number 1 or door number 2. And it was Schrödinger who suggested using the word entanglement for these unusual correlations between quantum systems. He also said it's rather discomforting that the theory should allow a system to be steered or piloted into one or the other type of state at the experimenter's mercy in spite of his having no access to it. And what Schrödinger meant by that is it's rather strange that we have these two qubits that are very distantly separated from one another, so there's no possibility that they're interacting with one another. Nevertheless, it's up to me to decide whether to open door number 1 of my box in Pasadena and then know what my friend will see when he opens door number 1, or to open door number 2 in Pasadena and then know what my friend will see when he opens door number 2. But Schrödinger also understood that these correlations, though different from classical ones, do not allow instantaneous communication between Pasadena and Andromeda, because when my friend opens his box in Andromeda, through either door number 1 or door number 2, he just sees a random bit, and that doesn't convey to my friend any information about the action I chose to perform on my box in Pasadena. Now, the theory of quantum entanglement did not advance very much for the next 30 years after that, until the work of John Bell in the 1960s. And with Bell, we began to think about entanglement in a different way, not just as something weird, but as something potentially useful, as a resource that can be exploited to perform tasks that wouldn't otherwise be possible. And we needn't go into the details, but what Bell described is a kind of game that two players can play. The players, Alice and Bob, are playing a cooperative game. That means they're trying to help one another win. And the way the game works is that the players, Alice and Bob, receive inputs, and they are to produce outputs which are correlated in some way that depends on the inputs that they receive. But under the rules of the game, Alice and Bob are not allowed to communicate with one another between when they receive the inputs and when they produce those outputs. They are allowed to make use of correlated bits that might have been distributed to them before the game began. And for this particular version of the game, if Alice and Bob play the best possible strategy, they can win the game with a success probability of 75% if we average uniformly over the inputs they could receive. But there's also a quantum version of the game where the rules are exactly the same, except now Alice and Bob are permitted to make use of entangled pairs of qubits that were distributed to them before the game began. And by making use of that shared entanglement, they can play a better quantum strategy and win the game with a higher probability of success, a little better than 85% instead of 75%. So they can use entanglement as a resource to accomplish something, winning the game, more effectively than they could if they didn't share quantum entanglement. And experimental physicists have been playing this game for decades now, winning with that higher probability of success that Bell pointed out the rules of quantum physics allow. And in fact, that experimental verification was recognized in the 2022 Nobel Prize in Physics. So these correlations, stronger than ordinary classical correlations, really are part of nature's design. Einstein derided quantum entanglement. He called it spooky action at a distance, which sounds even more derisive when you say it in German. But it doesn't really matter whether Einstein likes it or not. Nature is the way it's revealed to be by experiments, and we have to learn to love nature as it really is. So, boxes are not like boxes. We can win a game with a higher probability of success if we have quantum entanglement than if we don't have quantum entanglement. Was that really such a big deal? Yeah, it's a pretty big deal. And we can appreciate better why it's a big deal if we think about quantum systems with many parts instead of just two parts. We could imagine, for example, a book which is 100 pages long. And if it's an ordinary book written in bits, then every time you read one page of that 100-page book, you learn 1% of the information content of the book. And, excuse me. And after you've read all of the pages one at a time, then you know everything that's in the book. But suppose instead that it's a quantum book written in qubits, and the pages are highly entangled with one another. Well, what that means is that if you look at a single page, you just see random gibberish, which reveals almost nothing about the information content of the book. And even after you've looked at all 100 pages one at a time, you know almost nothing about the information that's encoded in that book. And that's because in the case of the entangled quantum book, the information isn't recorded on the individual pages. It's stored almost entirely in the correlations among the pages. And if we want to read the book, we have to make a collective observation on many pages at once. So that's the essence of quantum entanglement. And it's very different from correlations that we normally encounter. And what's so interesting is that these correlations are very complex to describe in terms of ordinary language. A quantum system that's highly entangled speaks a very extravagant language, which is different from the language that we understand or that our conventional computers understand. If I wanted to give a complete description of a state of a few hundred qubits that are in a typical highly entangled state, describing all the correlations among subsets of those qubits, then I would have to write down more numbers than the number of atoms in the visible universe. So it'll never be possible to fully express in terms of ordinary bits the information content of just a few hundred qubits. And that feature of quantum information, that we can't hope to describe it fully in terms of ordinary bits, was very intriguing to the physicist Richard Feynman. And it led him to make the suggestion over 40 years ago now that if we could build a quantum computer, a machine that processes qubits instead of ordinary bits, then it would be able to perform tasks which wouldn't be possible with ordinary computers. Now, Feynman's idea was that if we can't even express in terms of bits the information content of a few hundred qubits, then by processing the qubits, we would be able to perform tasks that an ordinary computer would never be able to emulate. And that idea was spectacularly validated a few years later by Peter Shor, who discovered examples of algorithms that theoretically we can run on quantum computers, which can solve problems that we think are too hard to solve for conventional computers. In particular, Shor studied the problem of finding the prime factors of large composite integers. We think that's a hard problem for conventional computers because really smart people have been trying for decades to come up with better algorithms for solving the problem. But the best algorithms that we have now require computation time, which scales very unfavorably with the size of the number to be factored. But Shor pointed out that if we had a quantum computer, this would be an easy problem, not much harder than multiplying numbers together to find their product. And when I heard about this in 1994, I was really awestruck, because it means that the difference between hard and easy problems, the difference between problems we can solve with advanced technologies and problems that we'll never be able to solve, that distinction between hard and easy is different than it otherwise would be, because we live in a quantum world, not a classical world. I thought that was one of the most interesting ideas I had encountered in my scientific life. And thinking about it eventually led me to change the direction of my own research from elementary particle physics to quantum information science. So does anybody care whether you can factor large numbers or not? Yeah, actually a lot of people do care, because the presumed difficulty of the problem of finding prime factors and of other related number theoretic problems, the presumed difficulty of those problems is the foundation of the crypto systems that we routinely use when we communicate privately over the internet. And if in a few decades quantum computers are widely available, we won't be able to protect our privacy using those same crypto systems. And so there will be a migration taking place in the next few years toward new crypto systems, which we think are going to be too hard to break even for quantum computers. And that will be an expensive process, which will play out over 15 years or more. But it'll be important to do if we want to protect our privacy in the coming post-quantum world. But the really fundamental thing that we learned from Feynman and Shor and others is that there's an intriguing classification of problems. There are problems which are classically hard, too hard to solve with conventional computers, but quantumly easy, which we can solve efficiently with quantum computers if we had them. And so it's a compelling question. What are the problems that are classically hard and quantumly easy? Factoring, we think, is an example of such a problem. And we've learned a lot about that classification of problems in the last 20, 25 years. I think we have a lot more still to learn, and our understanding of that issue will accelerate when we have large-scale quantum computers that we can experiment with. But if you're a physicist, there's a natural place to look for such problems, because we expect that a quantum computer would be able to efficiently simulate any physical process that occurs in nature. We don't think that's true of conventional computers, which are unable to simulate very highly entangled quantum systems. And that means with the quantum computer, we should be able to go more deeply into the properties of complex molecules and novel materials, which are very relevant for future technologies, and also to explore fundamental physics in new ways, for example, by simulating high-energy collisions of fundamental particles, or the quantum behavior of a black hole, or what was happening in the very early universe right after the Big Bang. One of the people who has contributed significantly to finding applications for quantum computing is my friend Eddie Farhi. A few years ago, after he wrote one of his characteristically brilliant papers, I was moved to write a poem which read in part, "We're very sorry, Eddie Farhi. Your algorithm's quantum. Can't run it on those mean machines until we've actually got them." And, you know, the poem goes on, but you get the idea. The point is that smart people have been working very hard for a while to develop applications for quantum computing. And for the most part, we haven't been able to run those applications yet because the quantum technology hasn't matured to a sufficient degree. So evidently, it's hard to build quantum computers. Feynman made the suggestion over 40 years ago. And quantum computers are just now getting to the point where we think they're starting to do interesting things. But what makes it so hard? Well, one of the fundamental difficulties is a phenomenon we call decoherence. Physicists like to envision a cat which is both dead and alive at the same time. But we never experience that kind of macroscopic superposition of distinguishable objects. And we understand why not. It's because a real cat that's both dead and alive would immediately interact with its environment, and the interactions with the surroundings would in effect immediately measure the cat and project it onto a state which is either completely dead or completely alive. That's the phenomenon of decoherence. And decoherence helps us to understand why it is that although quantum physics holds sway at the microscopic scale of atoms, nevertheless, classical physics provides a quite adequate description of what we ordinarily experience in daily life. Well, a quantum computer won't otherwise be so much like a cat, but it too will interact with its surroundings, and those interactions can drive decoherence, and that can cause a quantum computer to make errors and a quantum computation to fail. So if we want a quantum computer to work reliably, we have to somehow protect it from decoherence and other potential sources of error. Errors can be a problem even in the classical world. We all have bits that we cherish, and everywhere it seems there are dragons lurking who delight in tampering with our bits and flipping them. We've learned some ways to fend off those dragons when it comes to classical information. If I want to protect a bit that I especially cherish, I can store backup copies of the bit. And then the dragon might come along and flip the color of one of the balls. But I can ask a busy beaver to frequently check to see if all three balls have the same color. And when one differs from the other two, the beaver can recolor that ball so that all three match again. So if the dragon hasn't had a chance to damage two out of the three balls, the information is protected because it's been encoded redundantly. And even though errors occur, we can still recover the initial stored information. We'd like to use that same idea, that redundancy provides protection against error, in the case of quantum information. But at first there appear to be difficulties. As I mentioned, we can't make high-fidelity copies of unknown quantum states. So we can't, in the middle of a quantum computation, store the state of a quantum memory and save a copy in case our original gets damaged later on. Furthermore, there are more things that can go wrong with quantum information than ordinary classical information. If I have a qubit, it may be that the dragon comes along, opens door number 1, flips the color, and recloses the box. That's like a bit flip that could occur in ordinary classical information. But alternatively, the dragon might open door number 2 and flip the color and reclose the box. That's what we call a phase error in quantum information. It really has no classical analog. There's another way, though, of thinking about these phase errors. It might be that the dragon actually opens door number 1 of the box, and rather than flip the color of the ball, just observes the color and remembers it. And that will have the effect of potentially changing the color of the ball when we observe it through door number 2. And in many physical situations, it's easier for the environment to observe and remember the state of a qubit than it is to flip the qubit. And so these phase errors are particularly pervasive, and we have to find a means of contending with them. So really, the issue of errors in quantum computers stems from a fundamental difference between quantum information and classical information, namely that we can't observe a qubit without damaging it in some uncontrollable way. So if we want to perform a reliable quantum computation, we need to assure, since even if we don't observe the information ourselves, if it leaks to the outside world, that's just as bad. So we have to keep the information that's being processed almost perfectly isolated from the outside world in the course of a computation. And that's very difficult to do because our hardware is never going to be perfect. But we've understood theoretically how to protect quantum information from decoherence and other sources of error through the idea we call quantum error correction. And the idea is if there's a qubit, say, that I want to be able to protect, then I should encode that qubit using quantum entanglement in a highly entangled state of 5 qubits, say. And then if the dragon comes along and observes or damages in some way one of the 5 qubits, the information about the encoded state is not accessible to the dragon who looks at just one of the 5 qubits because the state is highly entangled. So by damaging that one qubit, the dragon doesn't inflict irreversible damage on the encoded information. And then we can have the busy beaver come along and make some collective observation on the 5 qubits, which will reveal which one of the 5 has been damaged and what needs to be done to correct that damage. And in doing so, the beaver also doesn't find out what the encoded information is, but only what the error is. So there's no irreversible damage to the encoded state. So the basic idea of quantum error correction is that if we want to protect quantum information, we should encode it very non-locally in a highly entangled state. The environment may interact with our quantum system locally, but just like when we were looking at one page out of 100 in that quantum book I described earlier, just looking at part of the system doesn't give access to the encoded information, so it remains protected. It's not irreversibly damaged. And furthermore, we've understood how to efficiently process information that's encoded in this very highly entangled way. So in quantum error correction, quantum entanglement is our friend. We might not ever see a real cat, which is both alive and dead, but we can envision encoding a cat using quantum error correction and preserving it in a delicate superposition state for as long as we please. So we developed the basic concepts of quantum error correction back in the 1990s. My student at the time, Daniel Gottesman, was a major contributor to that work. He was inspired to write a quantum error correction sonnet, which read in part, "We cannot clone, perforce instead we split coherence to protect it from that wrong that would destroy our valued quantum bit and make our computation take too long." And it's a sonnet, so it goes on. But you get the idea. We were really excited about developing the idea of quantum error correction, which I think is of just as fundamental importance for the future of quantum science as the discovery of fast algorithms like the factoring algorithm. It means that we should be able to control very complex quantum systems and make them do what we want them to do, even in the presence of noise, which is inevitably present. So what's the status of the technology now? There are a number of different approaches to physically realizing a qubit, which have been steadily advancing. The qubit can be encoded in a variety of different ways. It could, for example, be carried by a single photon, which is in either one of two places, or the spin of a single electron, which points either up or down, or the state of a single atom, which is either in its lowest energy state or some higher energy excited state that lives for a long time. Those are all remarkable encodings because the information is carried by an extremely simple single quantum system, a single photon or a single electron or a single atom. Yet we've learned to control those systems pretty well, thanks to several decades of technical advances. Or a qubit could be encoded in some more complicated system, like a superconducting circuit that conducts electricity without resistance at very low temperature. That's a rather remarkable encoding as well, because the qubit involves the collective motion of billions of pairs of electrons, and yet we can make it behave as though it were a single atom. So a central principle driving quantum information science is our firm belief that classical systems cannot, in general, simulate quantum systems efficiently. I think that's one of the most interesting things we've ever said about the difference between classical and quantum phenomena. And so there's a strong incentive to validate that in experiments to the extent that we can. And a few years ago, with some fanfare, the quantum group at Google announced that they had produced a quantum computer that could outperform the most powerful conventional computers at the time. And in a more advanced version of that experiment, which was done last year, what was achieved is that they constructed a quantum computer called Sycamore, which has 67 working qubits, which are laid out in a two-dimensional array, such that neighboring qubits in the array can interact with one another, so we can perform entangling operations on those pairs of qubits. And they executed a computation consisting of up to 32 layers of such 2-qubit gates, and then they measured all of the qubits to generate a string which is 67 bits long. To simulate what that quantum computer does with a classical computer is quite challenging. Now, remember, the device is noisy, It's not error corrected. And therefore, when we perform the computation, most of the time we just get random junk. But once every few hundred rounds, we actually get a valid result. And the computation can be repeated millions of times in just a few minutes, so we can extract a statistically useful signal. And that's the thing that's challenging to simulate. Furthermore, as we increase the number of qubits, the classical complexity of doing the simulation increases exponentially with the qubit number. So if we go to 80 or 100 qubits, it's far beyond what the classical computer can do if it tries to imitate precisely what the quantum computer is doing. Now, the particular task performed by Sycamore is not of particular practical interest except for the purpose of demonstrating the superiority of the quantum computer. But it's still kind of a milestone that the hardware has reached the stage where it can produce meaningful results in a regime where it's hard to simulate what it does using a conventional computer. I said quantum David versus classical Goliath because the competing classical supercomputer covers a couple of tennis courts and is consuming tens of megawatts of power, whereas the quantum computer is just a little chip comfortably nestled in a very cold refrigerator. It's useful to have a word for the current state of quantum computing technology, and the word NISQ has caught on. It's an acronym. It means Noisy Intermediate Scale Quantum. Intermediate scale is to remind us that we now have devices with of order 100 qubits, which are too hard to simulate by brute force using conventional computers. But noisy reminds us that these are not error-corrected devices, and the noise is a limitation on the computational power, on how large a computation we can perform and still extract a useful signal. For physicists, NISQ is exciting. It gives us a means of studying the behavior of very highly entangled systems of hundreds of qubits in a regime that we've never had access to experimentally before. And it might have practical applications which have economic value or a broader practical interest, but we're not really sure about that. We shouldn't expect NISQ to change the world by itself. It's a step toward more powerful quantum technologies that we're hoping to develop in the future. One paradigm of how we might make use of a near-term NISQ computer is a kind of hybrid quantum classical computation. It makes sense to use our powerful classical computers to the extent that we can, and then to try to boost that power with a quantum coprocessor. Well, it might work like this. We do a quantum computation of modest size, and then read out all the qubits to obtain a classical bit stream. We feed that classical information to a conventional computer. It returns instructions to modify the quantum computation. And that cycle is iterated until convergence, where the goal is to find some approximate solution to an optimization problem by minimizing a cost function. Now, we don't expect that quantum computers will be able to efficiently find exact solutions to the hardest instances of combinatorial optimization problems, but they might be able to find better approximate solutions or to find approximate solutions faster than conventional computers. So should we expect that NISQ machines will be able to outperform the best classical computers running the best algorithms to solve problems of practical interest? Well, we don't really know, but it's quite a lot to ask because the classical methods have been well honed over decades of development, and these quantum processors are just becoming available for the first time now. I think a fair assessment of where we are now is that NISQ has become valuable for scientific exploration, but there's no proposed application of NISQ computing with commercial value for which a quantum advantage has been demonstrated when we compare to the best classical hardware running the best algorithms to solve the same problems. And we don't have any convincing theoretical argument that we will see such commercially viable applications of quantum computing until we have quantum error correction and fault tolerance to deal with the effects of noise on the quantum computer, and that could still be some years ahead. If we do look ahead, and we imagine we had a perfect quantum computer that doesn't make errors at all, then we can somewhat optimistically anticipate that with systems of a few hundred qubits, we could run applications, say, to chemistry and material science that would outperform what we can do with the best conventional computers today. But the catch is that we don't have perfect quantum computers. The best quantum computers we have now, every time you perform an operation on a pair of qubits, makes an error with a probability which is just somewhat below 1%. Now we can foresee, over the next couple of years, having quantum hardware for which that error rate per 2-qubit operation is down to about 1/10 of 1%. But we'd like to run applications which have computations that are sufficiently long that will need a probability of error per step which is much smaller, 1 part in a billion or even smaller than that. So we need to bridge that gap from an error rate of 10 to the minus 3 to 10 to the minus 9 or better. Quantum error correction theoretically can do that, but quantum error correction has a very high cost in terms of overhead, how many physical qubits we need to provide sufficient protection against errors. It's reasonable to expect that for some of these applications, we would need thousands of physical qubits for each protected logical qubit, and that would bring the total physical qubit count up into the millions, which is a pretty big leap from where the technology is likely to be in the next few years with qubit counts in the hundreds or thousands. It would help if we could achieve much better error rates than that 1/10 of 1% that I said we can anticipate soon. There are some ideas about how the gate error rates could be substantially lower than that. And these are a few ideas that I'm partial to, and I won't explain them in detail. But they all have in common that to some degree, the protection against error is achieved at the level of the hardware design rather than being imposed by the software at a higher level of the stack. And these are all ideas in their early stages, and we can't say for sure how well they'll pan out. But it's really important to try, because if we could get much lower gate error rates, then that would extend the reach of quantum technology in the NISQ era before error correction, and it would significantly reduce the overhead costs for the error-corrected quantum computers that we're hoping to realize in the more distant future. So if we're going to get those much better error rates, one thing that will help are advances in materials science. With better materials, with better properties, we can, in principle, make better qubits. But advances in materials are hard to achieve, and the timescale for progress is hard to predict. And at any rate, we need more than just better materials. We need good ideas about how to make use of those material properties. So what will be the impact on the world if quantum computing does scale up to systems that can solve hard problems? I don't think anybody really knows. I think we have a limited ability to foresee what the most important applications will be for an entirely different kind of information processing. But based on what we currently understand, the most likely impact that we can, at least for now, foresee is on the study of chemistry and materials. Technological advance is often driven by progress in materials. Progress in quantum chemistry can lead to discoveries relevant for pharmacology or catalysts that will be better at capturing carbon or harnessing solar power and many other applications. It's not going to be quick, and it's not going to be easy. To realize our aspirations for quantum computing will require an investment of billions of dollars and perhaps decades of technical development. We need to do basic research and large-scale engineering, as well as the engineering that will make these systems work. So there's a lot of hard work ahead of us, but I think if we make that investment, we'll be amply rewarded. That said, I think it's a really exciting time for the field. I expect to see a lot of progress over the next 5 years, that we will probably see progress in quantum error correction accelerate over the next few years, that we can expect that with the new capabilities we have with NISQ technology for simulating quantum systems, we'll make new scientific discoveries. And there's a merging going on of the physics of many interacting entangled particles and measurement science. We anticipate that if we can control highly entangled matter, we can make more sensitive measurements of various kinds and build more accurate clocks and other applications. So I've been emphasizing today 3 main questions about quantum computing. Why do we want to build one? The best answer I think we currently have is that a quantum computer, we expect, will be able to efficiently simulate any process that occurs in nature. We don't think that's true for conventional computers, which can't efficiently simulate highly entangled matter. Can we really build one? We don't know of any obstacles that will ultimately stand in the way now that we understand the principles of quantum error correction, which should make quantum computing scalable to large systems. And how are we going to build such large-scale quantum computers? Well, I've noted that advances are being made on a number of different approaches to realizing quantum computing hardware. And I think it's important that we continue to pursue those different paths in parallel, because we don't have a clear understanding at this stage of what is the best approach to building a large-scale quantum computer that can solve very hard problems. It might be some hybrid of different technologies which fits the bill. Different technologies could find different niches, and so on. Now, I think these 3 questions make for a compelling research agenda, and a lot of what I've been thinking about for 25 years has concerned these questions. But I'm not an engineer, I'm a physicist. And what really excites me the most are the ways in which our ideas about quantum computing and quantum error correction are providing a fresh perspective on some of the deepest questions about nature. The way I look at the field of quantum information science is that we are in the early stages of exploring a new frontier of the physical sciences, what we could call the complexity frontier or entanglement frontier. It's different from the short distance frontier of particle physics or the long distance frontier of cosmology, which I worked on in the past. But like those, it's very fundamental and exciting. We are acquiring and perfecting the tools to create and precisely control very complex states of matter, highly entangled states of many qubits, which are so complex that we can't simulate them with our most powerful conventional computers or predict how they'll behave very well with existing theoretical ideas, and that opens opportunities for new discoveries. One intriguing trend in the last few years has been a surge of interest in quantum information ideas from the community of physicists who think about the fundamental properties of space-time and gravitation. Something we've been struggling with for decades is understanding black holes at a more fundamental level. How do we think about black holes as fundamental quantum objects? What happens to information that falls into a black hole? What's inside a black hole? We've made some progress on these questions, a lot of progress, I think, but we still don't have definitive answers. But the struggle to understand the properties of black holes gave rise to a remarkable idea called the holographic principle. Lenny Susskind of Stanford was a major contributor to this idea. And what the holographic principle asserts is that, contrary to our naive expectations, all the information in a room like this auditorium that's stored in our brains and our smartphones is actually available at the boundary of the room, at the floor and the ceiling and the walls, but in some very highly scrambled form that's hard to read. And what we've come to appreciate in recent years is that the geometry in the room, information about who's sitting in proximity to who else, is encoded in the structure of the quantum entanglement in that boundary description of what's going on inside the room. So in a sense, it's entanglement that is holding space together and defining its geometry. At a Caltech event, Robert Digraph, who was the director of the Institute for Advanced Study at the time, gave a talk about how the themes of theoretical physics are related to one another, and I was struck that he chose to put quantum information right in the center of things. He might not have done that a few years earlier, because the idea that quantum information is a unifying principle of physics has gotten traction only relatively recently. But where I would depart from Digraph is I'd erase the word theoretical, because quantum information is very much an experimental science. And if it's true, as we increasingly have reason to believe, that the geometry of space is an emergent property from some more fundamental description of the quantum universe, then we can anticipate that it will be possible to deepen our understanding of space-time and gravitation by doing experiments with highly entangled matter. It should be possible with experiments on a tabletop in a laboratory at a place like Stanford that study the behavior of very highly entangled matter to, in effect, create new universes and study their properties. So whether that prophecy really comes true or not, I think we can say with high confidence that many exciting and delightful surprises await us as we explore the entanglement frontier. Thanks for listening.
Thanks very much, John. We have now time for questions. First one over there, second one there. Yep.
I was curious to hear if you had any further opinions on measurement-based quantum computing or continuous variable quantum computing.
Could you, I don't see where you are. Could you raise your hand? Oh, hi. Yeah, say it again.
I was curious to hear if you had any thoughts or opinions on measurement-based quantum computing or continuous variable quantum computing.
Okay, the question is, what are my thoughts about measurement-based quantum computing and continuous variable quantum computing? So these are somewhat technical issues, but the idea of measurement-based quantum computing is that if we choose to, we can do a quantum computation by first preparing a certain highly entangled state of many particles, and then measure the qubits one at a time, but in an adaptive way where the measurement we choose to make on each qubit is conditioned on outcomes of measurements we did previously. But the cool thing is that once you prepared this resource state, then you only need to do single qubit measurements to realize a quantum computation that can solve any problem that quantum computers can solve. It's a really interesting idea. In some hardware platforms, it's a very enabling idea. One example is doing quantum computing with photons, where the ideas that have been proposed for doing quantum computation just with qubits encoded in photons require that we use this measurement-based approach. It's mainly because we can measure single photons pretty easily, but doing entangling operation on pairs of qubits is much more difficult. And we can prepare this resource state probabilistically. That is, we might not succeed every time, but we succeed with some probability, and so we can build it up in an adaptive way. So it's an important idea, and it might turn out to be a key to future quantum computing technology. The second question was, what do I think about continuous variable quantum computing? I like it a lot. So the idea here is I kept talking about qubits, which are different types of two-level systems. And the systems that we encounter in the laboratory are not necessarily qubits. They could be continuous variables. They could be things like harmonic oscillators, which have dynamical variables that can change continuously. It's possible to do a quantum computation using that type of system. But an important caveat is we want it to be robust. We want to be able to do error correction. And the only way I know how to do that with continuous variable systems is to encode a discrete system using the continuous variable system. And there are proposals for doing that. It was one of the examples on my slide that was suggesting, alternative qubit technologies. I think that's an important approach to pursue. Whether it will really be better than other approaches, of course, time will tell.
I have a question about errors that you mentioned that can happen at the base of the qubit and how you can entangle a few of them and encode them. So that way, in your terms, if the dragon even tries to see it, you can say, but what if there are multiple attacks on the qubits and multiple dragons at the same time?
Were you able to hear that? I'm sorry, I couldn't hear the question.
Oh, okay. So I was saying, if you have a few qubits that are encoded, right, and you have a dragon that is attacking one of the qubits, what if there is multiple dragons that are attacking the few qubits at the same time?
Oh, okay. So the question was about quantum error correction, and I always had one dragon in my slides who was damaging a qubit. But what if there are multiple dragons which are all damaging qubits? Well, if there, of course, there will be multiple dragons. We're going to have systems with many qubits, and so many errors will be occurring simultaneously. If we use the best codes, we can tolerate a lot of errors occurring simultaneously, as long as the number is not too high. So I guess I wasn't very explicit about this, but in order for quantum error correction to work, the rate at which the errors occur has to be sufficiently low. If it's too high, then that will overwhelm our ability to do quantum error correction. And in fact, when we do quantum error correction, that is itself a quantum computation which is subject to error. And so the theory of fault-tolerant, error-corrected quantum computing has to take that into account, and we need to be able to correct the errors faster than they are occurring, including the errors that occur during error correction. But that theory, by now, has become fairly mature.
Yes.
Yeah, I would like to hear your comment on the subtleties of comparing quantum advantage to classical simulation. So, for example, I know there are algorithms so the quantization or low rank problems or classical computers are amazingly good at that, and it's actually defeats some of the exponential advantage that quantum computers can incur. So, what would you think about comparing in this case with a lot of subtleties?
So the question was about what we call dequantization, and in particular, there has been a lot of activity in proposing and then compromising ideas for using quantum computing in, say, machine learning tasks in order to achieve an advantage over classical computation. And 5 years ago, there were several such proposals that looked promising, but then the classical team got to work and discovered that some of the quantum speed-ups that had been proposed for machine learning tasks could be partially lost just by using better classical algorithms. The quantum developments inspired better classical algorithms. The questioner spoke of low-rank problems. These are often problems that involve matrices, and if the matrices have a relatively low rank, then for many of the proposals for quantum machine learning having an advantage, they've been dequantized. So where does that leave us? I don't know. I think my view is that quantum machine learning is going to most naturally be applied to quantum problems. That if we're trying to learn, about probability distributions and properties of systems where we can expect quantum advantage, is where there's some quantum entanglement underlying the distributions that we're trying to learn. There may be, there are some proposals which are not without merit for how quantum machine learning might speed up other things which don't have anything directly to do with quantum mechanics, but I'm more confident about the applications to quantum systems.
Okay, question here and then there. Yep.
Do you think it's interesting to work on the question of the interpretation of quantum theory? And what's your take on that?
So the question is it interesting, or do I think it's interesting, to work on the interpretation of quantum theory? Well, sure, it's interesting. Lots of things are interesting. Now, when it comes to, my own interest is higher if ideas about the interpretation of quantum theory lead to experimentally testable predictions. And in particular, some people have suggested alternatives to quantum theory motivated by issues in the foundations of quantum mechanics and their interpretation. I think that's an interesting activity if those alternative models are experimentally testable. When it comes to just having an interpretation that makes us happy, that's also interesting. And I think it's more than just interesting. Different interpretations give you different kinds of intuition about quantum systems. So looking at quantum mechanics from the point of view of different interpretations can, in some cases, seed progress because it gives us a fresh way of thinking about things. So sure, it's interesting.
So I was curious, could you speak more to the current bounds of quantum computation, like what we have for Turing machines in classical computation?
So the question is, what can I say about the bounds on quantum computation compared to on Turing machines for classical computation? Is that what you said?
Analogous to maybe the sense of languages, regular or decidable and those types of things.
I see. Yeah, it's a good question. So one thing I didn't say in the talk, but maybe I should have, is that the question of what is computable as opposed to uncomputable, that is not changed by quantum computing. Whatever is computable with a quantum computer is also computable with a classical computer. Because it's possible for a classical computer to precisely simulate a quantum computer. I said it wasn't possible. What I meant was it's not possible to do it efficiently. So the big difference is not in what computations we can perform, it's how fast we can perform them. And in computer science, for a variety of reasons, we often make the distinction between problems that we can solve in time in a number of steps that scales like a power of the size of the input to the computation. So where one way of saying that we think quantum computing is more powerful is we think there are some problems that a quantum computer can solve with computation time that scales like a power of the size of the input, whereas for a classical computer trying to solve the same problem, although it's possible to do so, the computation time required is larger than any power of the size of the input.
Okay, one more question. Two more questions, one up there and one down here.
What's your estimate, the time it takes for the arrival of the first commercial grade quantum computer?
So the question is, what's my estimate for when there will be a commercial grade quantum computer? Of course, it depends what you mean by that. I think I know what you mean by that. Because, of course, there are quantum computing companies now, and they have products, and some people buy them. But I think what you meant was, when will there be a quantum computer which solves problems in which there's practical interest, where the solution to the problem has economic value, and we can't solve the problem with a conventional computer? And what's my estimate? Definitely more than 10 years, my estimate. Could be longer.
So one of my former students, Levin van der Sijpen, and a postdoc, Ike Chuang, did the first
They did.
Shor's algorithm. And I concluded, so I completely left that idea. I'm an experimentalist. And so it just seemed to me that the coupling problem, and then as that gets complicated, then the error correction and everything you need. And so I think it has just a limitation on how big you can make it. So that was my opinion 30 years ago. And I really appreciate your seminar or talk tonight. It's great. I haven't really followed that much of what's gone on since my days then.
Right. Yeah, that was important pioneering work that Ike and Levin did. And for a while, for the first few years, after Shor's algorithm was discovered, and there was growing interest in the experimental community in doing quantum computing with actual hardware.
Yeah.
NMR quantum computing was a leading approach for a few years. They were doing liquid state NMR, and it sounds a little ridiculous at first because these systems are really warm. They have high temperature compared to the energy splittings of the nuclear spins, and even in the presence of a large magnetic field. But the cool idea was that although the quantum state was almost completely random, there was a little departure from randomness that you could process. The trouble with that, or one problem with it, is it just doesn't scale well. As you try to increase the number of qubits, the signal-to-noise goes down sharply. And there actually are ideas about making it scalable. And theoretically, basically the idea is to cool the spins by doing the right kind of processing, and then doing the quantum computation on the nuclear spins that you've cooled. But let's just say that does not currently seem to be among the leading approaches.
Yeah.
All right, well, getting on. Actually, I was going to say thanks for unentangling for me.